Welcome back, students. Let's talk in this video about ethers and the reaction that we're going to see that makes ethers. Ethers have the functional group COC, meaning that you have a carbon group bound to an oxygen, bound to another carbon group. So if we see an ether, we're going to have an oxygen in the middle, and then we'll have a carbon group on either side. Ethers are going to be polar molecules, and thus they experience dipole-dipole forces. Remember this because at the beginning of the semester, we talked about different types of questions where we would give you a variety of molecules and ask you which one had the highest boiling point or to rank their boiling points. And that idea is linked to the intermolecular forces. So just a reminder that those kinds of questions are going to pop up again in this chapter. So you have to recognize that your ethers are polar because you have a carbon-oxygen bond that's polar this direction and this direction. And those individual bonds aren't everything that we're considering. We're looking at the overall shape of the molecule as well. So overall, the direction of polarity isn't these two individual arrows. We essentially do like a vector addition, and I'm going to erase those arrows and draw the overall electronegativity. This is the direction of polarity, where you have a partial positive over by where those carbon groups are, pointing to the partial negative over where that oxygen is. Because ethers are polar molecules, but they don't contain an OH, NH, or FH, then the strongest intermolecular force that they exhibit are dipole-dipole forces. Let's look at how we're going to make ethers. What happens when we make ethers is a reaction called the Williamson ether synthesis, and it's actually just two different reactions you've already learned put together. The first one is an acid-base reaction where you use a good base to pull off the acidic proton on an alcohol, right? So we just do this. When we pull off that proton, what we end up with is an oxygen with a negative charge. This thing is called an alkoxide. It has an alkyl group with an oxygen that's negative, right? That's where the word alkoxide comes from. The second step of your Williamson ether synthesis is to have this alkoxide, which remember has a negative charge, attack the alkyl halide in an SN2 reaction. Remember that this is backside attack, but in this particular case, it doesn't matter because you're not creating a chiral center where you would be able to illustrate the backside attack. You just want to make sure that you're counting your carbons and you're not adding too many or too few. And so now look at the end, we have our ether. Let's look at what the overall reaction is going to look like on paper. So on paper, you're going to start with an alcohol. You're going to add a good base. Here I'm using sodium hydride because I want to add a strong enough base so that I don't end up with an equilibrium at the end of that first step. So I'm purposefully using something that's stronger than hydroxide or another OR minus. Remember that sodium is just going to be your counter ion. It's a spectator ion. It's not involved in the reaction. Then in your second step, you're going to add your alkyl halide. Overall, your final product is going to be that ether that looks like this. Let's look at one other idea before we wrap up. In this last idea, I want to talk about how this is an SN2 reaction once you get to that second step. The first step was pulling off the proton, and when we pull off the proton, you get the alkoxide. Now, in our second step, we have to be careful about what alkyl halide we add. We need to add an alkyl halide that is not bulky. Why? Because if we add a bulky alkyl halide, something that is sterically hindered, then we're going to see a no reaction because this can't happen. We need to consider sterics for this second step because SN2 reactions are not going to happen at a tertiary substrate. So this part is going to be a no reaction. Let's wrap up. In this video, we did a super short overview of the functional group of ethers, and then we looked at the Williamson ether synthesis. We talked about how the Williamson ether synthesis utilizes a base and an alcohol to make an alkoxide, and then your alkoxide is used with an alkyl halide and an SN2 reaction to make the ether. Thanks so much for your attention. This is Katoni signing out.